Well, it's been a bit of a struggle. I'm trying to figure out exactly how spatio-temporal moments distribute themselves through space. In particular, I needed to figure out how many spheres of influence would actually more or less directly relate to any given central spatio-temporal moment. So my goal has been to determine something along the lines of the fabric of space. And what I've come up with is a way of visualizing spatio-temporal moments referencing a single nuclear example, which would be right here, in terms of how the various radii, which is represented right here, which would be basically the central point of any STM, would relate to other radii. And that would be all these other spheres around it. Now these spheres are actually what I would call spheres of influence. In other words, they have a way, their nuclei, if the spheres of influence are either tangential within or basically penetrate into a central sphere, then in some way those spheres would have the capacity to affect or be affected by it. So what I came up with was this idea that, hey, let's assume that all in normal normative space, let's say something like in the CMBR, which is the cosmic microwave background radiation space, where there's no matter. Basically, it is just waves upon waves of photons echoing throughout the fabric of space. If they were to be distributed in a manner that made sense, they would all be equidistant from one another to some degree. And every STM, spatio-temporal moment, would have a nucleus of some kind, a focal point at the center, and a sphere of influence. And that sphere of influence would be pretty much replicated throughout the entire matrix of the fabric, and the distance between all the nuclei would be regular. So I basically decided arbitrarily, and it doesn't really have to be the real number, and that has to be determined based on experimentation. And I'm thinking, by the way, of experimentation, that diffraction would be a very interesting way to approach this. Diffraction is a way of focusing photons without using a lens, pinprick in cardboard, for instance. Anyway, so what I decided was that we're just going to make all the matrix equally spaced in every direction. So a radius of 1/2 the diameter. So the sphere would be a unity, 1, and the radius would be halfway through. Now when I did that, I basically came out with what I call a horizontal distribution. So that's what you're seeing here, a horizontal distribution of spatio-temporal moments in the fabric of space. Now, to be accurate, I'm going to reorient it this way, and I'll show you why in a second. So every one of these nuclei is always 1/2 away from each other. And so I laid them all out on the paper, and then I created these spheres. And my real goal was not that I had already understood how you could have a central radii and you could have 6 other spheres touching around it. I'd already understood that. What I really wanted to know was how many radii were at a distance that they would either be touching the central sphere, which is what I call tangential, or penetrate it, which is right here. So, in doing so, I differentiated the blue ones, these blue spheres, as having a radius right here, which would just tangentially touch the central sphere. And I designated the red ones as having a radius that was equidistant by 1/2, like a triangle here, that would actually enter into the sphere. And we already, of course, have talked about the ones that all have a perimeter that touch the central matrix of any given spatio-temporal core, which, by the way, this is just one of these, but given special significance. So I ended up determining that basically you'd have 6 tangentials, 6 penetratives, and you'd of course have the 6 interpenetratives that actually reach out and touch the core of the matrix. So the next thing we're going to talk about is, so we got 6 and 6 and 6. That's basically 18. But this is all on a single horizontal plane. Let's go ahead and take a look at the above plane next. Okay, so as I move this sheet away, as I said, it's important that I reorient it along this axis, because as I do so, we are going to get a look at the spheres that associate with the central sphere, which is right here on the horizontal and the vertical. And here is our central sphere. So what I've determined initially was that they would be stacked on top of one another, right? That there would be a central sphere and there would be a tangential up here that would just touch it, right? Okay, so there is no such sphere that just touches it, because there's an interpenetrative right there instead. So, taking a look, these spheres all represent the ones that were on the axis, right here, where these lines are drawn. Then, what I did is I determined, in fact, there are 2 radially touching nuclei sphere above and below the central sphere's radial nucleus. So that's twice as many as I'd suspected. Then, because I recently discovered we have these interpenetrative spheres here, if you lay out everything using a half the radius triangles as the core of these spheres, that you would have 3 blue ones that interpenetrate right here. I'm going to do it here. 3 red ones that would interpenetrate the central core, and you would have 2 that are, I just previously mentioned here, the ones that touch the radius, and you'd have 2 more that tangentially touch the sphere of influence of the central core radius sphere of influence. Now if you look at that, you realize there's going to be 2 here and 2 here, because this is going to be symmetrical. So that's 4 to add to the original 6. So now we have 10 that touch the nucleus. In other words, these are the ones that actually get in touch with the nucleus in terms of the sphere of influence. These 2 are within a half radii, right? 1 and 2. 3 that penetrate into it, interpenetrative, and 2 on the perimeter that touch it perimetrically, and then you're going to double this number. So now we had 6 of these over here that were interpenetrating to the nuclear radius. We have 2 more above and below, so that's 10. Then we add to the previous number the ones that interpenetrate, which were 6 up here, 3 more, and you double that because it's going to be above and below because it's symmetrical. That's 6. So now you have 12 interpenetratives, and you have 2 tangentials, which just touch it here. Above and below is 4. You had 6 blue ones originally. That's 10. So now, basically what I'm saying, that around any centrally nucleated spatio-temporal moment, there is a total number of other spatio-temporal moments that normally would interact with it in terms of the reception and distribution of waveforms, photons. So let me go ahead over now to my little fabric of space sheet that I put together based on all of this. So here we have our distribution. It's very complicated. It's taken me quite a while to pull all this off. And here are my notes. In the fabric of space, basically, something that pre-existed the Big Bang was in complete passivity that demonstrated 2 fundamental characteristics: the capacity to draw themselves together and the capacity to keep themselves apart. So very much like stars, which have radiation pressure to make sure the stars don't collapse into a black hole, and at the same time have gravity to draw the matter in so that the matter can go through nucleosynthesis, creating the radiation pressure. This is the fundamental principle behind every STM. In the fabric of space, all nuclei are spaced by a uniform radius of 1/2. Now, in terms of our model here, there's only one central nuclei for our counting purposes. Each nuclei has a sphere of influence with a diameter of 1. In other words, if the radius of a sphere is 1/2, its diameter is 1. And this all lends to some mathematics, which I'll develop in a future discussion. Each nuclei has 10 proximal nuclei at a distance of 1/2. Basically, there are these 6, 1, 2, 3, 4, 5, 6, plus these 2 here, 7, 8, and 2 below, 9, 10. So now we have the number 1 and we have the number 10. Each nuclei has within its sphere 12 nuclei at a distance of the square root of 2. And that's just a triangular Pythagorean equation that has to do with the hypotenuse of a triangle. And in this case, the two numbers a squared plus b squared, 1 squared plus 1 squared, and then that's 1 plus 1 is 2, and then you take the square root to get the hypotenuse. So these are hypotenusal spheres, so to speak. There are 12 of those, and how do we determine that? Let me get to this here. We have these interpenetratives, right? We have 1, 2, 3, 4, 5, 6, whose radiuses are the square root of 2, which is about 0.707. Then we add 3 here, 7, 8, 9, and then the 3 below, 10, 11, 12. So now the number 12 has introduced itself. 1, then 10, then 12. Now, each nuclei has a peripheral contact of spheres of 10 at the distance of 1. So if we look here, and you look at these circles, the blues are peripherals. 1, 2, 3, 4, 5, 6. And then there's a 7, an 8, and a 9, and a 10. So the key numbers are 1, 2 sets of 10, and 1 set of 12. They all have to do with the fact that they somehow make contact with a central nuclei and its sphere of influence, and all of these work together to handle a wave of energy that could blow in from any direction and then distribute it out through space. The key being, if there's too much energy flux, they will collapse in on themselves, become entangled, and if the entanglement is stable enough, after the wave of super powerful energy passes, they will remain entangled as particles. And based on what limited knowledge of physics that I have, the particle that would be created would be a neutron. Within 10 minutes to 15 minutes, a neutron would break down into a proton, an electron, and an antineutrino. And now we have the beginnings of hydrogen that could then be used to fuel the stars. Well, that's my numbers. So a central 1 with 10 that have radiuses of 1/2, and I believe it was 12 within a radius of the square root of 2, and another 10 within that are just peripherally making contact that have radiuses that are at a point of, they just touch, so they would have to be 1. So you got 0, 0.5, 0.707, and 1 as the distance between each and every nuclei in a spatio-temporal matrix, which ultimately would comprise the fabric of space and time. Currently at work, radiating photons throughout the universe, but in the past were subject to such tremendous force outlet that it caused the creation of neutrons, which quickly broke down into hydrogen atoms, And there was so much energy, not only did it create hydrogen, it created helium and some lithium, perhaps trace elements of beryllium. I haven't really looked into it, but all those elements are called the astronomical primordial elements, which later were forged in the cores of stars to create all the known elements that astronomers call the astronomical metals. Well, there we go on this. We got some nice numbers together. We now have to explore the principle of how do these things actually get entangled, and that's going to take a good deal of thought. All right, carpe diem.